Hello, and welcome to Physics for Play. In this episode, we're going to begin a discussion that will eventually lead to us figuring out why imaginary numbers show up all over the place in physics. But to get to that point, we're going to start by talking about why trigonometric functions show up in physics. Let's get started. Before getting into the question of why imaginary numbers are useful, it helps to start with the question, what does simple harmonic motion have to do with trigonometric functions anyway? Aren't trig functions related to things like triangles and angles and the unit circle? And why are we paying attention to angles with simple harmonic motion when simple harmonic motion is just an object moving back and forth in a straight line? There's not really an angle there. Well, to answer that question, it helps to point out something that might be difficult to see at first, but we're going to show you why this is the case. And that fact is that simple harmonic motion is really just circular motion that gets projected onto one dimension. And we've put together a nice animation that kind of shows this. I'm going to slow it down a bit. And let's pause that. Let's pause that right here. So you can see, the thing I want you to pay attention to is this green dot right here. And as I play this animation, you can see the green dot moves around in a circle. It's just undergoing uniform circular motion. Now, if I pause that animation for just a second, you can see that the angle that describes that motion, or rather the vector that describes that motion, is a vector that I've drawn in blue here, and it has a length that I'm going to call A, and the angle that that vector is pointing at is given in yellow here, and I've written it as omega t plus phi naught, which is some phase shift. Now you might ask, why do I have this complicated form for it? And the complicated form comes because we don't start off at an angle of 0, we start off at some phase shifted angle. So at time 0, we start off at an angle phi naught, which is given by this yellow angle here. And as time increases, that angle gets bigger, which is exactly what you would get with this equation for the angle. So as time increases, the first term gets bigger. That means the angle gets bigger, which means the green dot starts moving around in the circle because the angle of the vector that's pointing to it is constantly increasing. Now you can start to see where we can start using trigonometric functions because we have a triangle here. I can break the vector A into components. If I look at the x component, let me call it the horizontal component because I'm going to use the variable x in just a second. If I look at the horizontal component of this angle in this triangle, well, that is the adjacent side to that angle. And by SOHCAHTOA, I know that the cosine is equal to the adjacent side divided by the hypotenuse, or equivalently, that the side length of the adjacent side is equal to the hypotenuse A times the cosine of the angle, which in this case is omega t plus that phase shift phi naught. Similarly, if I look at the opposite side to that angle, I can describe that again using SOHCAHTOA, using the sine function, because the sine is the opposite side divided by the length of the opposite side divided by the length of the hypotenuse. Or equivalently, I can say that this opposite side is equal to the hypotenuse A times the sine of the angle, which is again omega t plus phi naught. Now here, since we've been using x to describe our displacement, and since I'm projecting our displacement onto a vertical axis, I am going to say x is this opposite side, so it's actually going to be the vertical component here, not the horizontal component. And it's going to be represented by this green vector here. Now you can watch, and as the circular motion takes place, you can see that green vector gets bigger and smaller and bigger and smaller, and it points in the positive, then the negative direction, back to the positive direction. And the green vector is tracking the vertical position in that circular motion. Now I can project that motion, that circular motion, onto this axis, the vertical axis. You can see the green vector x equals a sine omega t plus phi. For the vertical component of the circular motion, just maps onto the component of simple harmonic motion for this green dot. And that green dot is just moving up and down in simple harmonic motion. And its equation is described by x equals the amplitude times the amplitude a times sine omega t plus phi. And you can see from the dashed line here, it's just a projection of the circular motion directly onto that vertical component. You can see the maximum value is the amplitude, which is the length of that vector a describing the circular motion. You can see it goes from a positive amplitude all the way down to a negative amplitude. So it really is true that simple harmonic motion can be described by uniform circular motion that just gets projected onto one dimension. So that's why you see trigonometric functions in simple harmonic motion, even though in the physical world there's not any actual angles that would suggest trigonometry. You can use trig functions to describe the motion. Now there's a problem with trigonometry. In fact, there are several problems with trigonometry. And if you've ever taken a trigonometry class, you've run across these problems because trigonometry is really hard. It gets very complicated because there are so many equations. So as I did in a previous video, I'm going to steal Paul Dawkins' trig sheet that you can find online. And there's over 50 equations on here. 50 different identities and formulas, half-angular formulas, product rules. It's just a mess. And I don't know anybody who has taken the time to memorize all of these because you're not going to live that long. And I don't think it's really worth it. So that's problem number one. And then even if I remember all of these different algebraic identities, if you want to do calculus with it, there's a whole bunch of derivatives you have to remember. So if I take the derivative of sine, you get cosine. If you take the derivative of cosine, you get minus sine. We can do the derivatives in Mathematica, but they're still messy equations that are just nasty to deal with. And it gets even worse if I start taking trigonometric functions times other trigonometric functions. You can see this just starts to get really nasty, and it's a giant pain. So much you have to remember. It seems like there's got to be an easier way. And it turns out there is an easier way because e to the x is a lot easier to deal with, and we're going to show you how to replace all of your trig functions with the exponential e to the x. E to the x is just a lot easier to deal with. If I'm multiplying two e to the x's together, well, I can multiply by just adding the exponents. And the derivative of e to the x is just e to the x, or if you throw a constant in there, you pull the constant down, but you still just end up with e to the x. As the old joke goes, the functions are all in a bar, and then another function comes in to warn them, and he says, the differentiators are coming, and all of the functions run away, except for one lone function sitting at the bar, and the warning function comes in, and he says, hey, didn't you hear me? I said the differentiators are coming, and the function just sits there sipping his beer and says, well, I'm e to the x, because nothing happens to e to the x when you take the derivative. It's a magical thing. So e to the x is a lot easier to deal with than having to memorize these 50 different trigonometric equations. And it turns out that we can use e to the x along with complex numbers, so along with numbers that contain the square root of -1, and we can use that to dramatically simplify the math it takes to solve differential equations, linear differential equations for things like simple harmonic oscillators. We are going to pause here for now, but join us next time where we'll show you how to relate complex numbers and complex exponentials to solve simple harmonic oscillator problems and to do it in a way that's easier than using trigonometric functions. Like the video if you liked it, and if you'd like to see more of these, please click subscribe.